All right, so let's get started. Okay, so it's my pleasure to introduce Sandro Tacchella today for our astrophysics seminar. Sandro did his PhD in 2017 at ETH. And after that, he did a 4-year postdoc at CFA, working with Lars Hörnqvist and others. And then he went, then he got the call as an assistant professor, went to Korea to JWST, and then a year later joined the ranks of faculty at Cambridge University, and so where he is still at the moment. And so I should say that Sandro is really well known for lots of things in galaxy formation. He has worked both, very strongly on the observational side, but also on the theoretical side. He has made contributions to understanding the main sequence, galaxy quenching, things that's called compaction, if you know what I mean. And he's also very productive, having published over 100 refereed papers within the last 10 years. So it's quite amazing. Today, Sandro will talk about another kind of topic that he's heavily involved in, of course, the James Webb Space Telescope. Okay, Sandro, please.
Thank you, Robert, for a very kind introduction. So let me just word this, whole technology nowadays. Okay, so good morning. Thank you very much for coming. So I will be talking about kind of cosmic dawn, trying to understand what we see currently with the James Webb Space Telescope, kind of what we have learned over the first year. So I will be diving in with you in kind of some of the deepest images we have been taken from space, kind of probing really the early formation of galaxies. And so you might say, well, but these are not, of course, not the images that probe kind of the first structure of the universe. For this, we would have to go to the cosmic microwave background. And indeed, the cosmic microwave background is one of the fundamental pillars for the evolution of our universe. And from the CMB, but also other fundamental measurements for observational cosmology, we know nowadays that today's energy budget is dominated by dark energy. We have, when we look at the matter, the dark matter component that is dominant, and the ordinary matter today makes only about 5% of the energy budget. And so for today's talk, this is giving us basically a good understanding for the initial conditions for galaxy evolution. I will not be talking much about cosmology, but of course, if we assume now, for example, that we have only dark matter in the universe and evolve basically initial conditions from the CMB forward, we can come up with maps such as those. This shows you the dark matter structure at redshift 0 from the Millennium Simulation Project. And you can see basically that, the universe is maybe homogeneous on large scale, but when you go to the smaller scales, we can see a lot of structure. We can see overdensities, galaxy clusters, and then dark matter halos, where we believe the galaxies are living in. And one of the success for cosmology is, of course, that we can now look and we can actually measure the distribution of galaxies in the space. We can do redshift surveys, starting out, at the CFA, but then also, around the world. And you can see basically that the large-scale structure, as observed here, shown in blue, is very consistent with the large-scale structure that such simple N-body simulations predict. Now, what is the paradigm for galaxy evolution then when we add baryons to it? So to first order, we can summarize this with these 3 points, where we say that we have these tiny fluctuations in the early universe. They are growing, so we have built up these so-called dark matter halos. The baryons are attracted to these dark matter halos. They are able to cool and really condensate in the central regions of these dark matter halos and then form stars. Now, an interesting thing is that we need actually to regulate this growth. So feedback from stars and black holes are needed to prevent, overcooling, basically the formation of too many stars. And you can see this quite nicely if you look at the number density of galaxies as a function of stellar mass. So here, the blue basically shows you what we observe in the local universe. So it shows you the number of galaxies as a function of mass. And if we are rescaling the dark matter halo mass function by the baryon fraction, so basically assuming that all the baryons, all the gases forming stars, we get this red dashed line. And you can see that, you need to kind of regulate the growth both at low halo masses and at high halo masses so that you are, reproducing the galaxy stellar mass function. Very similar, you can see actually that you can come up with the same conclusion when you look at the right figure, which shows you the U minus R color, which is thus corrected here as a function of stellar mass. And what you can see is basically SPI modality in the color distribution. We have the blue star-forming galaxies at the bottom left. And on the top right, we can see this red sequence. And again, when you think about a cold dark matter universe where the structure is building up from the bottom up, right? So from small structures to larger structures, you would expect that the largest structures are actually the ones that formed most recently, most intensely, but you can see kind of an inversion of that, right? You see the most massive galaxies are actually quiescent. So you need, again, somehow to regulate the growth, you need to stop the star formation in the most massive systems. And you might say, okay, well, we have a paradigm, so what's the problem? Why, haven't we solved galaxy evolution yet? Well, I think one of the fundamental challenges is that galaxies, and the physics of galaxies plays on a wide range of different spatial scales. So we have the large-scale cosmic web, the environment, which is on gigaparsec scale. And then we have the dark matter halos, and you have to really zoom in into the very central regions because galaxies are only, of a size of a few kiloparsecs. And then when you think about galaxies themselves, they are made up of actually a lot of interesting components. We have the star-forming regions. We have, the formation of individual stars, right? And then we also believe that in each of the galaxies, we have a supermassive black hole in the core. And again, if you look at the, the spatial scales, they are, tiny. They are the size of parsecs or subparsecs, and then all up to the gigaparsec scale. And so, I just write down here a few of the processes that we think are important for the evolution of galaxies. And it starts really out with kind of the small scale processes where we have the formation of stars, but then also the feedback, the stellar feedback of stars. We have, black hole formation and growth, but also how the black holes then, kind of lead to energy output and, black hole feedback. And the problem with these processes is that they couple on many different spatial scales. And then, of course, you can go up all to the large scales with, a lot of questions about how important, for example, magnetic fields or cosmic rays are. And again, this is happening on a wide range of different spatial scales, but also a lot of different temporal scales. And this is something that is important throughout my talk, as you will see. So moving on to the observational side, we might say, well, okay, we can just observe galaxies and see how they evolve as a function of time, right? And the idea is that we can use powerful telescopes, and we can basically study objects that are further and further away and therefore look further and further back in time. And so indeed, for example, with Hubble, we have been probing, back to, 10 billion years or even further. And so we are able basically to see how the galaxies in the universe evolve as a function of time. And so we can come up with diagrams such as this, which shows the cosmic star formation rate density in the universe. So this shows the amount of star formation, so solar masses per year, per co-moving volume. And you can see when we go back in time, right, we can see that the cosmic star formation rate density actually increases. And there was a peak around a redshift of 2, or, look back time for down 10 billion years. And then before that, the cosmic star formation rate density has been decreasing. And so when we think about the timeline of the universe, we had, the CMB, around redshift of 1,000, recombination. Then we entered the dark ages. And then we think that, somewhere around redshift 20 or so, a few, maybe 100, 200, 300 billion years after, 100 million years after the Big Bang, the first stars and galaxies started to form. So we have the cosmic dawn epoch. And then there was this huge transition going from a neutral to an ionized universe, starting the epoch of ionization, up to cosmic noon. That was kind of the epoch where most of the stars in the universe formed. So great. So we have mapped out, with a lot of data, the star formation rate density. But of course, an important caveat here on the observational side is that this doesn't really show you the evolution of an individual object, right? So this shows you basically kind of a volume average. And so when we look back in time, we actually observe always different galaxies. And so if you are a physicist and you ask the question, well, how does a galaxy evolve? It's the problem observationally is really that we cannot just look at a galaxy today and the day after tomorrow, and we don't see any change, right? We see always different objects as a function of look back time. And so connecting those is very challenging, because again, over our human lifetime, the dynamical timescale of galaxies is much too large. So that's why a lot of the very fundamental questions, related to galaxy evolution are still open. For example, how do galaxies actually regulate their star formation? How do these feedback processes from stars and black holes, kind of lead to the evolution of galaxies? How do the quiescent galaxies evolve? How do galaxies chemically enrich and build up their elements? How does the morphology of galaxies evolve? And then when we move to earlier times, how did the first black holes and first galaxies form and evolve? And also, how do these different sources contribute to the reionization of the universe? And so today, I'm happy to chat about all of them. So feel free, to chat with me about any of those. I will focus in particular, kind of moving more towards the earlier cosmic times, understanding black hole growth and galaxy growth at early times, and also discuss kind of the morphology of galaxies. And if you're interested in chemical evolution and so on, I'm happy to chat about that as well. So what's kind of the simplest model we can come up for the universe? So what I've been like to do actually is taking up simple structure formation models where we have, for example, a cold dark matter universe, and we are trying to ask, well, how do we have to populate the galaxies? And so we can come up with these simple regulator models where we have gas inflow, some prescription for star formation and outflows. And so in these kind of models, you basically can set the star formation to be proportional to the accretion rate of gas, right? So the more fuel you have, the higher the star formation rate. And so you can say, well, okay, let's try to build a simple model based on lambda CDM. So you have a dark matter accretion rate given by this right term here. You multiply this by the baryon fraction. So this gives you roughly, the inflow of gas. And then you have a star formation efficiency that gives you then the star formation rate of a given dark matter halo at a given redshift. Now, again, this is a simple model. So we just assume that the star formation efficiency doesn't change as a function of time. So it's just, a function of halo mass, and there's no redshift evolution. And so you might say, well, okay, how do you, from where do you get that? And of course, you can run very complicated simulations to get that, or you do it empirically. So you basically go and say, well, let's look at the UV luminosity function at redshift 4, where basically everybody would agree what that is. And then you're getting a star formation efficiency out of that. And you can see that, the star formation efficiency increases a function of halo mass and peaks around 10 to the 11 solar masses of halo for a halo mass, which is consistent with this kind of, when you compare the dark matter halo mass function with the galaxy stellar mass function at redshift 0, basically. And so if you do such a model, you're actually able to reproduce. Now my slide, okay, good. It's just a time delay. When you look at the cosmic star formation rate density as a function of redshift, now we're just focusing on high redshift 4 and above. You can see that such a simple model, even though you just fit it and you're basically tune it at redshift 4, you are able to reproduce the evolution of the cosmic star formation rate density out to redshift 10 over 2-3 orders of magnitude. And again, this just shows you basically that the buildup of dark matter halos is very important to understand the evolution of the cosmic star formation rate density. So how can this be understood? Well, it's basically, to first order a convolution of the star formation efficiency with the halo mass function, right, which is shown on the right side of the y-axis. And what you can see when you plot the halo mass function, you can see that from redshift 10 to redshift 4, you can see that the star formation, that basically the halo mass function is moving into this regime where we have now 10 to the 11 solar mass halos more abundant at redshift 4, right? So you really increase the number of halos that are able to host effectively, efficient star formation. And then, of course, you have, an additional contribution coming in because these halos also have higher accretion rates and therefore a higher star formation rate. So this is this. And then, of course, you can also build other models where you can say, for example, the star formation efficiency changes as a function of redshift, and you would get a much higher cosmic star formation rate density. And again, we basically are interested to understand, well, what's the star formation efficiency? What is the structure formation, doing at redshift 10 and above? And for this, of course, we need to find galaxies at these early times. And so how can we do that? Well, one of the most popular techniques is the so-called dropout technique that has been used a lot by, with the Hubble Space Telescope. And the idea is that basically because of the high neutral fraction between us and these galaxies or in the intergalactic medium, there is a strong absorption of all the photons that are basically shortward off the redshift at Lyman alpha break. So you can see basically there's no detection in the blue bands, and then only you pick up galaxies in the red bands. And so this is basically the photometry for GNZ11, which also had a Grism redshift, determined by Pascal Auge. This galaxy is around the redshift 11, as I will see later in my talk as well. And the idea is that, yes, you know, it's not detected at 1.2 micron, then at 1.4 micron, it starts to be kind of apparent, and it's clearly detected at 1.6 micron. And the challenge with Hubble, you know, was that, well, at 1.6 micron, you don't get any data anymore. And so you had to go to ground-based photometry, which has much larger uncertainties, and then to Spitzer with IROC. And there, the problem was also confusion, right? You see that the resolution of the image was quite bad, so you're not really sure if this redshift 2 contaminant up there on the left contributes to the flux of this high redshift galaxy. So that's why we built a new telescope, and that telescope is the James Webb Space Telescope, $10 billion, so it's a pretty expensive telescope. I myself am part of the NIRCam science team, so we built basically NIRCam, and I've been working a lot on the software development over the last 5 years. And I'm leading now the data reduction for the NIRCam team for the GTO program. I will not bore you with data reduction things and issues that we are struggling with, but if you're interested in scattered light effects and all these things, I'm very happy to chat with you about that. So why is JWST cool? Well, first of all, it has a larger mirror, right? So you can collect more light. But of course, more importantly is now we also have coverage much further into the infrared, in particular probing the near infrared, which helps us to characterize these high redshift galaxies in much greater detail. And I think most importantly is actually the spectroscopy, as you will see in my talk. It's the first time we have really a spectrograph in space. And so the leap forward in time is like, you know, the sensitivity that we have, the increased sensitivity we have now in space from pre-JWST is roughly, when you think about certain spectroscopic modes, is roughly a factor of 3,000. So this is like the same way as, you know, you go in the optical telescopes from Galileo's telescopes to the VLT, right? So the discovery space that you're opening up is really huge. And again, there is a huge team on the NIRCam and NIRSpec science team, and I will be talking in particular about the JADES survey, which is the JWST Advanced Deep Extragalactic Survey, which is a survey where we try to optimize both the imaging and the spectroscopy. Okay, so the idea is that we are using imaging to you know, find interesting objects that we have not known before, and then we use spectroscopy to characterize them in better detail. And so you want to really optimize these both modes. And that's why this looks rather messy. So this is basically our survey takes mostly place in Good South and Good North. And you might say, Sandro, why did you make such a complicated mosaic? You know, it looks horrible, right? But the idea is to really, you know, invest these 800 hours and optimize the time to get basically first the imaging, and then basically, you know, get spectroscopy slightly offset and in parallel, and then basically move stuff around and get spectroscopy for the thing that we had imaging before. And so this is the best way we could optimize the instrument and the telescope. And you see that there's a lot of data taken around the Hubble ultra deep field, but we have actually additional very deep pointings just slightly off of that as well. And you can see the depth now, you know, basically we extending what we had done with Hubble to the infrared. So we are going to up to 5 micron, yeah. So I mean, like, so that this field, Good South and Good North, have a lot of data, right? We have observed these fields with a lot of VLT data. So for example, we have very deep Muse mosaics in those fields, you know, of 100 hours. And so if you want to do, for example, Lyman alpha, H alpha cross correlations, you know, these are very interesting, those fields. But basically the ancillary data in those fields is unique, right? Coming from the X-rays all up to the radio. And so that's why we really want to focus on those fields. Now, of course, we try to also have other pointings, and this is something important to, well, maybe, let me just say we had also the first data release, and you can actually click on the link, and, you know, if you do that, you can actually, I don't know if this is a good idea, but let's just go there. You can go and surf around the data, and you can basically, you know, move around and discover the data yourself. There is also other layers. You can see, for example, you know, where do we get spectra from? And you can click on the spectra and you can see, for example, these are, you know, redshift 6 galaxies and so on. It's like, you know, you can just move around and play around with the data on the public website if you're interested. And it's also fun for outreach, I think. But of course, you know, JADES, as you can see here, is part of, you know, other surveys that are done from, you know, Primer, Cosmos, WDeep, and Sears. And again, the idea of the community is, of course, to this kind of wedding cake strategies where you say you have, wide pointings that are shallow and only few filters to much deeper pointings. And I think Jade's here, goes deep, but also wide. And what we do is we have basically 14 different filters. So we have really, wide range of filters. And again, the spectroscopy follow-up is crucial, I think. So this is showing you one of those images. This is at 1, 2, and 4 micron. And again, this is just a few tenths of arc minutes across. We can zoom in, and you can also look on my screen later on. But the richness of structure is just really amazing. And you having been used to look at Hubble images, you might say, oh, this galaxy looks like a redshift, 0.5, 0.7 galaxy. But all of those galaxies are actually redshift 2, 3, and 4. It's really amazing, actually, of how far we can see. This shows you a comparison, for example, what we have seen with the Hubble in the I band. You can kind of see there is some structure here, but then if you look at, at 2 and 4 micron, you can just see this grand design spiral galaxy at redshift of 2.2. So it's really amazing. This shows you basically the Hubble ultra deep field. This is the deepest image we had at 1.6 micron here on the left with Hubble. And this is now, in a few hours, basically at 1.5 micron with JWST. And you can see that it's not just the depth that is better, but also the sharpness, right? You can see this when you look at the upper right galaxy, you can start seeing this kind of star-forming clumps at redshift 2. And so it's really cool. And again, the spectroscopy is really unique. We use different gratings, so basically different resolutions, so that we can actually not just observe the whole spectrum, right? So you can get everything from line alpha up to S3, but you can also go and zoom in on individual emission lines and see whether they have broad components, which are important for HGNs, but also outflow physics. And I think the biggest step forward that we made was actually last year, where, in the fall, in October, we got actually, a year ago, we got the first images. We reduced them in a few days, and we tried to find new galaxies that are at high redshifts. And so there were these 2 galaxies already being high redshift galaxy candidates, with Hubble, because these are kind of in the deep part of the Hubble ultra deep field. But then we also had 2 other galaxy candidates at redshift 12 and 13 that we thought that might be high redshift galaxies. And then a week later, we got near spec observations. We put those galaxies on the slit, and we were able to successfully get a redshift from this. And here are the spectra. And you might say, well, they don't look that convincing. The thing is, we are pushing over JWST in the first few months to its limit, basically, right? So we have here, the units are 10 to the minus 21 ergs per second per centimeter square per angstrom, right? It's really faint stuff. And so you can see basically how we determine the redshift here is based on the Lyman break here. And again, they are very consistent, not perfect, but they are consistent with what we estimated from the photometry alone based on the dropout technique using photometric redshifts. And having those distances, then what we did is we then go and measure the cell population properties of those galaxies. And what we find are galaxies having a stellar mass of the order of 10 to the 8, 10 to the 9, and star formation rates of about 1 to 2 solar masses per year. So this means that these galaxies roughly double their mass every few tens of millions of years. And this is nothing like peculiar if you think about simple, galaxy formation models at these redshifts. One thing that is what we try to do also from the imaging is actually to measure the sizes. The sizes, what we do is basically we don't measure them on the mosaics, because on the mosaics you always suffer from correlated noise issues. And so what we do is we forward model each individual exposure, and we have written a special tool to do this on the GPU side. And I'm happy to talk more about this. It's called Forceful. And we find our sizes of the order of 50 to about 150 parsecs. So these galaxies, as you can see on the image, maybe they're really, really compact. And when we now go and infer star formation at surface densities, we see that these star formation at surface densities are of the order of what we see actually in local ULERGs, right? So although the star formation rates themselves are Milky Way-like, they are in a very compact configuration. Yes. Half-light radius. Yeah. Yeah, so that's a very good point. So we try to model this also with multiple components and so on, and we don't find any convincing evidence for that. And so we have like a limit on that. So basically, we can say that yes, 50% of the light or of the star formation is included in that. Then you could have a floor that extends further out. Yeah. Yeah, exactly. Yeah. Well, yes, redshift, surface brightness dimming is one of the key worries in these kind of works. Yeah, I agree. So, okay, then let's move on to GNZ11, which was an object that we observed then in February, which has been known already in the literature actually for many years. So Richard Bounds back in 2010 already found it in the NICMOS data, right? So alpha camera 3, right? A very old detector on Hubble. And they were saying, well, there's no evidence for being detected at any wavelength shorter than 1.6 micron, right? They only see it in the H band. And so this may suggest that it's a transit or spurious source because it was super bright. Like they saw it and they were like, well, that's such a bright source, and it's only detected at 1.6 micron. It cannot really be a redshift, 9 galaxy, but they cannot really rule it out. And so then Pascal has taken, has been obtaining many more data points, more, with alpha camera 3, better data, and also IRAC data. And they basically in 2014 put it back on the high redshift galaxy candidate list. And then with the GRISM on Hubble, they were inferring basically a Lyman drop around, 1.4 to 1.5 micron. And so they're basically, measured a redshift of 11. And again, why is this galaxy so special, right? You can look at this plane of absolute magnitude, okay, which is, brightness versus redshift. And you can see this galaxy lies up here to the right? This is about 3 times L star at redshift 7, but at redshift 11. So this galaxy is super bright. And so the question is like, why is it so bright? Is it an HEN? Is it the distance wrong? Or what's going on in this object? And so we have been observing this galaxy both with NIRCam, but also NIRSpec. And I've been writing several different papers because this object is actually very, very interesting. So I want to give you a bit of an overview of what's going on. When we look at the images, the first thing we did is actually look of whether there are other galaxies in the vicinity. And you can see these arrows, right? So they are pointing to galaxies that are within 5 co-moving megaparsec around this galaxy. These are only photometric redshift, so you should be a bit suspicious, but we are trying to get spectroscopy now for them. But indeed, this galaxy is not alone there. Okay, it seems that there are other objects nearby. And I think the most astonishing that came out, for this object, but also from NIRSpec in general, I think, was the spectrum for GNC11. I mean, you can just see basically now, well, obviously this galaxy is at, not redshift 11, but redshift 10.6. And you can see this with this very strong Lyman alpha drop, but then also many emission lines, right? All up, to basically oxygen 3. Again, this is at, very distant. I mean, it was mind-blowing when we look at the spectrum, because of course we saw first the other spectra and we're like, yeah, what do we see now? But obviously, like, it's much brighter. And that's why the units here are different, right? This object is just much, much brighter than the other fainter objects above, redshift 10. So you might say, Sandro, okay, don't show me the photometry. It looks super boring now. But, the photometry itself is still interesting because actually what we did is, of course, we confirmed the redshift, but we are able to now characterize the spatial distribution of light. So you can see that it's compact, but we are able to, again, forward model the galaxy in different components. And so if you squeeze your eyes, you might see that, in particular 2.7 micron, you can see maybe a slight extension here to the left. And then when they look at the galaxy itself, you can actually decompose the light in a central point source and an extended component. So we fit this galaxy with 3 components: a central point source, a slightly extended source, and then this haze component to the upper left. And so we try to understand, what is these different components made of? Again, the point spread function is very important to understand, both on the on the mosaic, but again, because we do the forward modeling on individual exposures, the PSF is actually much simpler, which helps us again with the modeling side. And so what I show you here is basically the SED for the point source and the extended source. And what I've been doing is basically trying to see whether we find any indication whether point source is an HEN or not, or the extended source can be explained by just star formation. And what we are able to do is actually with Prospector, with an SED fitting code, we are able to reproduce both SEDs, the one for the point source and the one for the extended source, with normal stellar templates and with dust absorption and some gas emission. So we don't need to invoke some weird population 3 stars or any HEN contribution. And so the idea is that what we see actually is that the central point source is outshining the galaxy. So the luminosity, in particular terrestrial UV, is a factor of 3 dominated by the point source, and the galaxy, the underlying extended source, is about a factor of 3 times fainter. And so the stellar mass, on the other hand, if you look at the SED, because of this color at 4 micron, is actually dominated by the central point source. So what we find is that this galaxy has of the order of 10 to the 9 solar masses. Most of the mass is in the extended component, but the luminosity is dominated by the central point source, and you can describe it with a very strong, kind of increased star formation history. So having kind of a nuclear, formation of a bulge or a lot of star formation activity in the core. But if you look at the spectrum more closely, so with Roberto Maiolino, we have been then trying to understand, well, can we find any indication for an HEN activity in their core, right? So the SED itself is fine with star formation, but if you look at, for example, the neon lines, you can see neon 4, and then you can see other lines. For example, when you look at C4, you can see kind of a P Cygni feature, which implies outflow velocities of about 800 to 1,000 kilometers. And also the semi-forbidden lines, here basically you can see that they're all pointing towards a rather kind of very high density environments. And so all of this together basically makes us more and more convinced that actually what we're looking at in the center is actually an HEN. Okay, and actually we're looking at the broad line region of an HEN. And so if you now take the magnesium 2 line or the N4 line and you infer a black hole mass, you're finding a black hole mass of the order of about 10 to the 6 solar masses. So again, this is a rather massive black hole, but it's actually quite nice to see and assume now how does it connect backwards and forwards in time. If you would take such a black hole at redshift 10 and assume Eddington accretion, you are able actually to get black hole masses that are consistent with the quasars we observe at redshift 6 and 7. And if you evolve backwards in time, if you evolve with Eddington accretion, you see that you're kind of getting around redshift of 10 into 20 to a redshift, a stellar mass regime, a black hole mass regime of about 10 to the 3, 10 to the 4 solar masses. And if you have super Eddington accretion, you're able to go even further down to lower masses. And again, the stellar masses, I think the stellar mass for this object is quite well determined. The black hole mass, of course, has its uncertainties. But overall, we find this black hole, when you look at the scaling relations of black hole mass and stellar mass, we see that such a black hole lies slightly above such relations. And so we have been going after many more, searches of black holes. Actually, what the idea here is that we are looking at for broad components in the Balmer emission, but not in the oxygen 3 emission, right? Because if you see it in oxygen 3, you would say that it's probably an outflow. And so we're just looking into the broad components of Balmer emissions. And we are finding of the order of about 12 black holes in the JADE survey by now that have black hole masses somewhere around 10 to the 5 to 10 to the 8. And when you look at scaling relations, again, the uncertainties are large, but they seem to be kind of more in the upper left side. So, they are rather massive black holes given their stellar mass. But if you look at things such as dynamical mass or this, velocity dispersion, they're kind of moving back down onto kind of what we see in the local universe. Now you say, okay, great, there's so many HENs, and indeed they are common, but not everything that is a point source and red is actually an HEN. And one of the challenges, I think, to find them is related to the BPT diagram that we are all kind of used, in the local universe, right? We're looking at the excitation of those lines and say like, oh, it's an HEN regime. The problem is that because at these redshifts, the metallicities are much lower, all these objects actually move into the left side of this diagram. So they look like normal star-forming galaxy, actually. And they're only identifiable based on kind of the broad components we are observing in the emission, in the Balmer emission. And then again, not every red point source is an HEN. We actually also find many brown dwarfs that have not been known before. They can mimic the SEDs of these high redshift galaxies and these high redshift objects very well. So you have this break, and then you have basically kind of a blue slope, and then a strong peak towards the near infrared. And again, we basically try to understand those stars better because they are an important contaminant both in the HEN search, but also in the galaxy search at high redshift. And one way to identify them is, of course, with proper motion. And this is one way of how we have actually identified many of them. Again, the nice thing is we have exquisite HST data there. And that's why we want to go to these fields where we have studied it before. And you can see basically in the Hubble image, the thing was here, sort of shown by the red point. And now, a few years later, this thing has moved over there. Okay, so it's obviously moving around. Okay, so let me move. So I talked a lot about now a few galaxies at high redshifts, right, where we have both spectroscopy and photometry. Let's move on to the galaxy population overall. And so, in the first few months and actually first year, there were a lot of papers coming out related to finding some of these high redshift galaxies. And again, these are mostly photometric searches. So these are only photometrically, identified objects, and not many of them have spectroscopic follow-up. But there seems to be an indication that the UV luminosity function doesn't evolve anymore much at the highest redshifts, indicating that there might be too many UV bright galaxies at early times. And so indeed, we have also been doing similar searches. So this shows you basically what we have known before JWST. And this shows you now what we have with JWST, right? So we're talking here in our field in JADES, in Good South and Good North, over 125 arc minutes squared, we have of the order of 700 galaxies. And only the ones with black dots have a spectroscopic confirmation. So the 4 of them, or basically the 5 of them I've discussed now. The other objects, we are trying to get spectroscopy before, but it's hard. It's actually quite inefficient. You have to go very deep, and you can only observe, a few for every exposure you're taking, just because they are scattered on the sky and the field of view is small. What is very interesting is actually looking at their morphology, because again, they are not all point sources. The highest redshift objects seem to be very point-like, but if you already go to redshift 8, 9, you start seeing that these galaxies come in quite rich substructures. And so it reminds me a little bit of these clumpy galaxies we have been finding at redshift 2, right? And so like, oh, everything is in clumps and mergers. But then when you go and take, longer wavelength data, you see the homogeneous mass distribution. And again, if you look at the redder bands, you can see that typically they're looking quite smooth, but the blue light, the rest frame UV is much more clumpy. So I'm currently working on understanding the stellar populations of these galaxies and basically infer things such as the cosmic star formation rate density. Again, this is very preliminary, and I'm just working on this. But we find that the cosmic star formation rate density is decreasing, but then at the highest redshift, there seems to be kind of a leveling off. And the question is this really real? Is this just some scatter that we have, or is that, is that physical? If it's physical, it might be, related to some of the processes I will be discussing now. So let me quickly, give you a bit of a heads up regarding these early galaxies and whether they are breaking our universe, our cosmology. And I think there are 2 interesting points that are slightly different. One of them is basically saying that there are too many high redshift massive galaxies, in particular around redshift 5 to 10. And the other thing is to say something about there are too many UV bright galaxies above redshift 10. So these are slightly different, and I will try to address both of them. So let's first focus on massive galaxies. So what is the problem? Well, the problem is basically saying, well, let's look at the field of view, and let's try to understand what's the most massive galaxy you could observe, right? And so this is a work we have been doing with Chris Lovell. The black dashed line basically shows you what we would expect for these typical surveys of different areas if you would assume that basically all the baryons form stars. Okay, so this is like a hard upper limit, basically. But if you take a galaxy formation model such as Eagle, we would expect, basically the typical mass to be much more on this dashed, this dotted line. And what you can see is that in these early works by Labbe and Naidu, we found that these galaxies are indeed very, very massive for their redshifts. And you can see that they are basically lying on or above this line, which means that you need more baryons than you really have in the universe to produce these massive galaxies. And so then, of course, the question is, well, should we change lambda CDM? And I think my answer would be no, because there are so many challenges when we infer stellar masses at these high redshifts. So first of all was actually is the distance. Okay, so these early claims are all based on photometric data. And we know already that this galaxy redshift 16 actually moved to redshift 4 point something, around redshift 5. And all of those galaxies still need spectroscopic follow-up. For these galaxies where we found, where we have actually spectroscopic follow-up, those galaxies actually show a clear HEN contribution. And similar to, to GNC11, but many other objects, we think that actually the SEDs might not just be pure stellar emission, but actually have contributions of HEN, which can also change your stellar mass estimate significantly. Another important caveat is actually bursty star formation. We think that a lot of these galaxies at early times have actually increasing star formation histories. There's kind of an observational bias, right? We are observing, when you look at an image in the sky, you see the bright galaxies, and usually these ones are the ones that are young. They're increasing their star formation rates. And then it's actually very difficult to infer what the underlying older stars are. How many are there? And so understanding exactly how to correct for this outshining effect is a big challenge. And then, of course, the stellar population model related to IMF and binarity, you can move these points by factors of 2 or 3, just changing the IMF and the binarity fraction in these galaxies. Okay, let's move on to the other question about like the earliest galaxies and whether there are too many bright galaxies. So this goes back to the star formation efficiency, figure that I showed you earlier. And, one thing to note there, I think, which I, want to highlight now maybe first, is that if you look at redshift 10, you can see that the halo mass function is very steep, right? Again, you change the halo masses by a factor of, 3, right? And you're changing the number density by 2 orders of magnitude. It's important to see how steep that is. And so this means that if you have any kind of scatter, doing something crazy in very few objects at the low mass end, they can scatter up very easily and dominate whatever you see. And so this is a paper that we have been putting together with Jacob Shen, where we try to understand, well, if you take such a simple halo model, let's just, introduce more scatter to it, okay? And the scatter, here is just basically the relation of how we go from halo masses to the UV luminosity. And you can think about this scatter in halo formation times. It can be a scatter in the star formation variability, or it can be a scatter related to the stellar populations and the amount of dust, right? All of these things can introduce scatter in your modeling. And what you can do is basically in this canonical, point, which is showing you basically very little scatter and the default IMF conversion, we are basically down here. And so you're very inconsistent with what we would observe at high redshifts. But if you start increasing the scatter, by a factor of 2 or 3, you start suddenly being consistent with what you observe spectroscopically or photometrically at a kind of redshift 10 to 12. And so the idea is maybe that, we have an evolving scatter where we are at high scatter, this shows you the UV luminosity density or the cosmic star formation rate density. So you are able to reproduce the highest redshift points by just having a lot of scatter. So for example, having very bursty star formation. And then you are basically moving towards kind of more, continuous star formation and therefore less scatter. And you're able to reproduce the overall shape of the cosmic star formation rate density quite naturally. Yes. Well, you could say I just changed the star formation efficiency. So if you, for example, you can also build a model where you say, let's assume that the star formation efficiency depends on metallicity, and the galaxies at highest redshifts are really, really metal poor. So you are very efficiently forming stars. In principle, you can also come away with that. But here we are basically just introducing a scatter. Yes. Yes, exactly. Yes. No, exactly. So you need to boost it. You need to boost, and you can roughly see by how much, quite significantly. Okay. No, it's I think it's Mach. It's Mach magnitudes. I think, yeah. You can look at the paper. The exact definition is written, but I think it's magnitudes. It should be units, yeah. Okay. So that's that. The other thing, of course, we can also change London CDM. And actually, we have played around with that. At that time, with a student at Harvard, together with Sonak Bose. And at that time, we were like, oh, yeah, let's change the simple model and just introduce warm dark matter cosmology and see how things would change. And not so too surprising is like there's this very strong degeneracy between the baryonic physics and the dark matter model. We can change to a warm dark matter cosmology and just increase the star formation efficiency and get the same cosmic star formation rate density as with a cold dark matter universe where we have less efficient star formation. And this is shown here, and it's something that basically just highlights that I think before we claim to break lambda CDM, we should really understand the baryonic physics. How much time do I have left? Like 5? Sorry? 5 minutes. Okay, so let me move on to kind of the morphology in the last 5 minutes. So again, the structure of galaxies, are shaped by a wide range of different processes, including mergers, kind of the angular momentum of the accreted gas. And so it's important to understand like how do galaxies look at the earliest cosmic times as well. And so I've been doing a lot of work, in particular during my PhD here, at ETH Zurich, is basically understanding how we can use what we obtained from Hubble and combine this with ground-based IFU observations. So kind of understanding where the stellar mass is, where the young stars are, and relate this to the kinematics obtained with H alpha. And so moving now to high redshifts, I think JWST really showed, the power that we're able to do morphology now, really also at redshift 2 and above, right, where we start probing the rest frame optical now. So the first thing is, that we actually are observing bars, even at redshift, above 1. This galaxy is at redshift 2.1. We also have these very interesting galaxies that are basically invisible in the Hubble, right? These are these HST dark galaxies. And then they start, appearing very nicely in JWST in kind of the reddest bands at, 3 to 4 micron. And many of them have this kind of disc-like shape. Okay, so I say disc-like shape, they look like discs, but they might not be discs. So they seem to be this flattened thing. And you can even, throw AI onto images and try to find these elongated structures. And there are many elongated structures at earliest cosmic times, which are, above redshift, 3 or 4. And indeed, there have been papers written now to study basically the disk fraction. And I would be, again, careful of whether we call this a disk or a kind of an elongated, elongated ellipsoid. But basically, there seems to be disk galaxies, above redshift 4. And if you compute of how much star formation is taking place in them, there seem to be the dominant population. And so what we have been doing is we have been focusing actually on a single galaxy at redshift 7.4. And again, the challenge there is that these galaxies are very, very compact. And so we have to, take into account the point spread function, okay? And so what we have been doing is basically forward model the light distribution of this galaxy up there, for which we have a nice spectrum, which shows basically that everything is a normal star-forming galaxy. And when we measure the stellar population of this galaxy on the integrated scale, we find this galaxy is of the order of 10 to the 8 solar masses with a star formation of 10 solar masses per year, an actively star-forming galaxy. It seems to have a clumpy structure, but even more interestingly is that we have a very interesting color gradient in this galaxy. And so this is now after basically doing the the PSF homogenization. So you don't see the PSF effects here. You see really pure color gradients. And you can see that basically the color from 2 to 4 micron is increasing. So you have a kind of a, some kind of increase in flux here, but then you have a decrease in color when you go to this, to 2.7 to 3.6 micron. What this indicates to us is that basically there seems to be a strong emission line around, 4 micron, 4.1 micron when you go towards the outskirts. And you can see this here, right? This corresponds to basically what we see in H-beta and oxygen 3. And so the question is, what is driving this color gradient, and what can we learn about the stellar mass and star formation distribution in this galaxy? And so again, we have been forward modeling this galaxy in 3 different components, a core, a disk, and this clump. And then we have been performing SED modeling. This is work led by William Baker, a PhD student at Cambridge. And then we have been inferring the stellar populations of these different components. And what you see is, again, that these galaxies are compact, but they are clearly extended. The core, we find, the half-light radius of the order of 140 parsecs. For the disk, it's towards 500 parsecs. And what we see is that the star formation histories are slightly different. The disks seem to be going up very rapidly, whereas the core is kind of more constant. And so we have been able to, change or measure the star formation rates and stellar masses for those components, and then basically infer how the stellar mass profiles. So this is stellar mass density as a function of radius, star formation rate density as a function of radius, and the specific star formation rate as a function of radius. And what you see is that the stellar mass, not too surprising, is kind of dominated in the central region by the core, and only the disk dominates in the outskirts towards a kiloparsec, whereas the star formation is mostly dominated by the disk component. And if you're looking at the specific star formation rate profile of the combined profile, you see that this is increasing as a function of radius. And so we see that in the center, this galaxy is still forming stars, but at a kind of a slower rate in comparison with the outside, so that you're basically doubling your mass in the outside every tens of millions of years, whereas in the core, it's in slightly longer timescales, maybe of the order of 100 million years or so. And so this is interesting because now we can start trying to understand, well, how do these galaxies grow and basically end up at redshift 2, where we actually have a lot of more measurements from Hubble. And so this is shown here on the top right? If you would take, and this is a very simplistic assumption, you take basically the distribution of star formation now and just integrate it up. And you can see that such a galaxy that is very compact now just keeps growing and actually devolves quite nicely onto the size-mass relation of quiescent galaxies at redshift of 2. Okay, so you don't need to change much, actually. You can just keep this galaxy growing inside out slightly, not by much, but by a factor of 2 or 3, and then this galaxy ends up very nicely here on the size-mass relation. But again, more interestingly is, of course, this crazy comparison of thinking of like how much stellar mass has formed in this core. And I show you here the stellar mass surface density as a function of radius. The orange line shows you this redshift 7 galaxy. And the interesting thing is, if you compare this to local ellipticals, you can see that this galaxy formed about, a factor of 2 or 3, the amount of stellar mass that you need in the core of such a galaxy. But you are basically missing, a factor of 1,000 in stellar mass in the outskirts. So again, it just highlights basically this, that these galaxies at early times seem to be very compact, formed, a lot of stellar mass in the very central region, but miss out, of course, a lot of mass in the outskirts. Okay, so the last minute is just like diving into kind of what we also can do with contaminants. This galaxy here is ARC 227, which is a galaxy of the order of 10 to the 10 solar masses at a distance of about 35 megaparsecs. And so when I reduced this data, I started out up there and then, this field and then moved slowly in. And I saw a lot of green points. These are not these green points, but, you can see at 2 micron, a lot of emission. And I was like, what are all these green points? Is it like a problem with the data reduction? And what we figured out is that these are actually stars of this object here. Okay, so they're basically stars in the outskirts of this galaxy that scatter all up to the viral radius of this object. And again, this is just seen basically because we get these very, very deep images. These integration times here are of tens of hours. And so we have basically diffuse light measured from JWST directly. We can go to the Dragonfly instrument from Yale and Toronto to measure the diffuse light. And then from counting individual stars, we're able to do surface brightness profiles of this object, basically down to a magnitude limit of 35 magnitudes per arc second squared. So it's really, really deep. And so the idea now is, of course, to understand why do we see these kind of shelves in this galaxy. And again, it can be quite nicely explained actually with mergers. And this is interesting, right? Because if you have these low mass galaxies and you're probing 1 to 10 mergers, you're starting to probe an interesting regime from a cosmological perspective. And so again, we can explain these shelves with simple n-body simulations, minor merger models, where you basically have these 1 to 10 mergers and you have several of them to explain basically this kind of shelf-like behavior in the very outskirts. This is just to show you, you have your interest in these very high redshift galaxies, but there's also a lot of stuff we can do at lower redshifts. Okay, so I think I have to wrap up. So I think that indeed we are probing now the very first galaxies with JWST. I think that there are not yet very strong evidence for breaking lambda CDM. There is, of course, a lot of interesting questions related to how do these first galaxies regulate their star formation, how variable is the star formation, and we can come up with quite simple baryonic or observational explanations, whether we have too many UV bright galaxies or too many massive galaxies. But overall, I think it's important, it's fruitful, but also necessary to combine both imaging and spectroscopy. So thank you very much for listening. Yeah. Mm-hmm. Yes. So from our observations, basically, we can get a rough estimate of the black hole mass based on the broadness of some of these emission lines. And then you can try to estimate the bolometric luminosities, and then you basically can infer what the Eddington luminosity and Eddington ratio is. Oh, they don't go too high. I mean, you can look at the paper. They go up to, I mean, like they are distributed around Eddington, and we also find so many sub-Eddington black holes. The highest ones are of the order of a few, so we're not talking of more than 10, never. So it's like 2, 3, 4, basically. Yeah. Yes. So you see, like for me, the problem is always like first we have to define what we mean with the star formation efficiency, right? Whether we talk about an integrated star formation efficiency, basically stellar mass of black hole, or is it like the gas accretion and how much you convert of this gas, accreted gas into stars, or is it actually the gas mass that's already in the system and you convert that into stars? So there are small differences there. So you see, like we can by tuning up the scatter, and it's maybe too much, but if you tune up the scatter with very variable star formation, you can come up with these simple halo models where you don't need to change the star formation efficiency, actually. Okay, so you might say that, this is the star formation efficiency that relates the gas accretion rate to the star formation rate, okay? But if you define a different star formation efficiency, for example, how many stars formed within a dark matter halo, then yes, that would shoot up. But this is just because you introduce the scatter that leads, to maybe, more, gas, for example, in a different configuration, so a bursty star formation. Yes, exactly. Yeah. Yeah. Yes. It depends really on the data you're having. Okay, so you see, like a lot of this early data uses these white bands, and there, you have really hard time to see whether to first order the infrared whether something's a brown dwarf, an AGN, or a very massive galaxy. Okay, and again, if you get better data, of course, if you get spectroscopy, it's easy to tell apart. Even already medium bands will help, or time-dependent data. So you can rule out the brown dwarf scenario. You can then start looking at the AGN. But even if you see it's an AGN, then it's really difficult to actually estimate the stellar mass of that component. You can try to do it space resolved, as I kind of showed for GNC11. But again, for many galaxies, they are so compact, it's actually difficult to differentiate what is the stellar mass of the AGN itself. You need to kind of subtract the AGN contribution. Yeah. So I think in the next few months, a lot of these very massive galaxies will get spectroscopy, and then we will have much better estimates. An additional complication, even if you say like, well, they are galaxies and there's no AGN, there's no brown dwarf, even if I take these SEDs and model them slightly differently. So for example, allow for a variable dust attenuation law, then we basically can get down, stellar masses that are a factor of, 3 or 4 lower already, right? So, so it's not just about these different, whether it's AGN, brown dwarf, or a star, or a galaxy, but even when you say, okay, it's a galaxy, the SED modeling has a lot of uncertainties. Yeah.
Yeah, so first of all, the results, the images are mind-blowing. Of course, this is huge for the future. I think it's very exciting to talk really presented that way. I wanted to know if you had some comments on this haze that's in GNC.
Yes. Yeah, so no, unfortunately not, is the short answer. In the sense of like, so I extracted the SED and I fitted the SED and I can come up with, so it can be consistent with being something close to GNC11 itself, so kind of a merger structure. But it can also be consistent because the SED is very, noisy. It can also be a low redshift 4-5 emission line galaxy, very strong emission lines, basically. That's why we only see it in a few bands. But it could also be a background galaxy that might be lensed. But I think, we have done very rough lensing calculation. I think it's very unlikely, but in principle, it could also be something in the background. We have taken IFU data, and it's not very clear from that data as well. We get hopefully more IFU data, so we maybe be able to extract the spectrum of this specific object. When we look at the IFU data, we find actually even slightly further up, not the haze, but slightly further up, an emission line in the cube. And it's when you think it's associated to GNC11, it will correspond to helium. So it's perfectly spot on. And we don't see anything else there. So that's why we interpret it as maybe population 3 stars. But it's very uncertain because, of course, it could also be something at lower redshift. It's not consistent with any of the solutions for the redshift 2 galaxy because it lies between GNC11 and the redshift 2 galaxy. But so it's not the haze, but it's kind of a region here that just shows it seems helium emission at the moment. Okay, and it's not consistent. Even if you assume it's an AGN, that GNC11 is dominated with an AGN, you cannot explain that the ionization, the brightness of helium based on the AGN emission. So it's a population 3 region candidate, and we have to get better data. Yeah, so we are following up these structures now, hopefully in the next few months. Yeah. Yes. Yeah. Yeah, it depends whether you ask my theory head or my observer head, right? I mean, on the observational side, I think we cannot make any strong conclusions. So basically here we are trying to demonstrate, a technique that we try to apply for a larger set of galaxies. Okay, so it was like the first time we're getting this kind of data, we try to, do this forward modeling and the SED modeling, and we try to improve on the statistical, first of all, it's interesting to try, not just from the data analysis point of view, to forward model each individual exposure and try, to take into account in the interpretation the covariances you get for the two components, and also, fold this into the SED models. There are a lot of technical developments we did on the observational side. And so this is where we currently are with our estimates and our uncertainties. And so indeed, we find that there seems to be a very dense, massive core, and the star formation is not that you have less star formation per unit area, but you basically have specific star formation rate that is lower in the center towards the outskirts. And when you look at the timescales for this based on the star formation histories that we infer, which are very rough, I think this happens on, 10, 20, 30 million year timescale. So short, you see. So I'm not sure if that's like a very structure, that is, coherent over several dynamical timescales. So it can be kind of something that is more like breathing or so. But again, we don't go into this much in the paper because it's very uncertain. But if you have statistics, if you are able to do this for a mass complete sample in a few years, then we might be able to say something more sophisticated. Yeah.
To HST, so I remember, so some of these very high redshift luminosity function and high redshift galaxies were obtained using strong lensing to magnify the background.
Yes.
Is this something that is done with JWST as well?
Yes. So there are several fields that are observed, and there's in particular one program called Uncover, where he's a co-I of. So they basically try to do this technique, and data is being taken both on the spectroscopic side and on the photometric side, and the key there is indeed to probe kind of the faint end, right? So you want to combine basically what you learn from the lensing together with these, kind of wide and deep fields, so that you can really map out the luminosity function over, all the magnitudes. Yeah, but that's something that is being done. There you have lensing uncertainties coming in as well, and they are not negligible. But it's something worth doing, I think, because you probe at least 2 magnitudes fainter.
Then we get a luminosity function up to what redshift?
Well, if you're brave, you can go up to redshift 20 in principle. Now, what I didn't have time to talk to you about is that, I think up to redshift 12, we can get very robust UV luminosity functions now with JWST. Above redshift 12, with the filter sets that have been chosen till now, I think it's very uncertain. And this is because when you look at the Lyman break, where it moves, to this regime where you have only these wide band coverages. And so you see a galaxy in this band, but not in this band. But the problem is really how sharp is this decrease, in the flux of the galaxy spectrum, right? Is it really a break that points towards the high redshift solution, or is it kind of a softer decline, which might be consistent with a dusty, crazy emission line galaxy at lower redshift? And so what we have been designing now is a medium band survey where we just point for 100 hours in good south to basically probe exactly this wavelength range with many medium bands, so we can measure the strength of the decline. And the data has been taken over the last weekend, and so we are reducing it at the moment. And so we're trying to basically get the first UV luminosity function constraints that we think are robust at redshift 15. So I'm working on this at the moment. It has a lot to do with, also understanding the completeness and so on. And these are things that are getting better the more experience we have with the data. Yeah. So yeah, I think we can go up to redshift 15 with JWST, and then beyond that it gets trickier and trickier. But I'm sure we will hear claims.
Then I found your also very interesting last stuff that you showed with where essentially are able to resolve, if I'm saying correctly, individual stars in galaxies that are about 35 megaparsecs.
Oh yes.
Object, understand?
Yes.
I mean, is this like could this be an effective way? I mean, because of course, James Webb is very expensive to get time on, but could this be a possible way to detect, let's say, stellar streams along like Milky Way coast? I mean, at really low surface brightness, like 33 max.
Yeah. I think not. The field of view is too small. I mean, so I think Charlie is brave, and I think they try to do these kind of things around other dwarf galaxies. But you're talking here of for a single object, if you want to map it out a little bit more than what we have here, you're talking of like 200 hours. So it's really expensive. Okay. Here, what we have been doing is it's just this is from the Blue Jays survey. It's a survey where you actually want to do spectroscopy, and we get parallel images. And so we were just like, yeah, we are in the cosmos field. So we took these 2 pointings kind of at arbitrary locations, you see. And we thought that it might be useful, for the community because it's in cosmos, right? And you have primary imaging and all this other imaging. And so it was really a coincidence, you know what I mean? And yeah, you can try to go just for this, but it's challenging. You're in a 100-hour plus regime. So I don't think it's super effective. But the Roman Space Telescope is coming along soon, right? And you have a much larger field of view. And you don't need to go really beyond 2 micron for doing that, right? I mean, like you want to make sure that you identify stars and not globular clusters or other, background galaxies. So there are a bit of certain color cuts you want to make. But if you go just towards 2 micron or maybe 2.5 micron, you can actually select stars quite efficiently. Yeah.
Okay. Any more presentations? Right. So, Sandro will be taken out for lunch. For lunch at the web of 12:30. So if you want to join, and I don't know whether there's still lessons for the from the regional or okay, so let's give Sandro what we can.
Yeah, thank you.
Okay, so